We have end of the week with another seminar on physical oceanography. I'm probably sick and tired from the faculty search, physical oceanography, but this is going to be a good seminar given by Buckingham. He started his career in Grove City College in 2000, and then he continued in Johns Hopkins University, and he did his PhD in University of Rhode Island. And now he's in Southampton and working. So his interest shifted from search for zonal jets, which is what he did on Rhode Island. Now he's looking on submesoscale processes, which is one of the strands in Southampton. And I know his PhD advisor and all what they're doing, so it's really nice work. And I'm glad that he's here, and we'll give him the word.
Thank you, Boris. Yeah, thanks. So can you hear me okay? Well, thank you very much, Boris, and thank you, St. Petersburg, for inviting me to come give a talk. So as Boris said, I am a postdoc at the University of Southampton in England. I work with an individual named Professor Alberto Naviero Garabato, and we do submesoscale stuff together. So this is kind of it's been about a year since I've talked about this stuff. But I thought given Boris's field of study, and then the fact that it's kind of a little more mature than my present work, this would be a better topic to talk about. So this is in collaboration with my advisor, Peter. Fabian Schlosser was a postdoc at the time, and Kelsey Obenauer was an REU student. So that's one of those undergrad summer students. So this work actually stemmed from her summer studies. So those are really valuable programs if you don't have one here in Florida. So without further ado, I'm going to talk to you about these bands or these jets that we observe from satellite data today. So I want to give you a few definitions before I do so. So but what do I mean by multiple zonal jets? I mean alternating eastward and westward currents. Mid-latitudes, I'm referring to the subtropics, about 20 to 50 north and south, observed from space, so the focus is on satellite measurements. And then finally, there's going to be a kind of a relationship between mesoscale eddies and these patterns, and so I want to define kind of outright what mesoscale eddies are and what I mean by those. And those are namely that we see westward propagating features in the mid-latitudes or subtropics that have, that are mesoscale, so they're about 100 kilometers in size. And they're seen from the altimeter record by Dudley Chelton, among many other people. So this includes Rossby waves. So I'm not discriminating between linear and nonlinear, if you know that whole discussion. So just before I get started, how does two-dimensional turbulence or planetary scale turbulence differ from homogeneous turbulence? This is just a little schematic. So you can kind of imagine a wind or a current blowing over a little rough topography. That generates a large-scale eddy that then cascades. That's the phrase that they use. The energy cascades to smaller and smaller scales. So here I'm talking about things that are on the order. This differs from, so we say energy cascades. This differs from near 2D turbulence or at the planetary scale in that the wind and the currents feed energy to larger scales. So this, you can kind of look at imagine you're looking at the surface of the ocean from space. So you'd see eddies that, if you could somehow see the cascade of energy, you would see this. So these are like scales on the order of 100 kilometers. So we say that energy cascades to larger scales. So as a side view, this will be tricky because throughout the talk, the red is not showing up. So this is actually a red arrow. So we'll see what happens when we get to the images. So this is kind of like a side view of that. So a Taylor column you could think of, and they're rotating. So the energy goes to larger and larger scales. So this is just a schematic of what I'm referring to. So at some early time, you might have lots of small eddies that then coalesce and feed the energy to larger and larger scales until finally you get this very large feature. So this is two-dimensional turbulence. Now, you can represent that in this diagram so that three-dimensional, the x-axis here is the zonal wave number, and the y-axis is energy. So we say that energy in three-dimensional turbulence at the small scale goes to smaller and smaller scales. But at larger scales, planetary scales, the energy goes to larger scales. Does that make sense? And so what happens here is actually a topic of interest that Boris and I were talking about today. And the work that I'm doing now is quite related to that. So you would refer to this as the submesoscale, some unknown thing. And then in addition, entropy in two-dimensional turbulence goes to smaller scales. So entropy is just squared vorticity. So I'll start with this quote. It is very unlikely that a strongly turbulent fluid can be understood even in the mean until the nature of its energy-containing eddies is rationalized. So Peter Rines, who's kind of one of the founders of zonal jet theory, or geostrophic turbulence theory, said this quote, and the reason I include it is just to emphasize that the ocean, although we think of it in this very laminar kind of, conveyor belt kind of flow, and even in the subtropical gyre type flow, it's very turbulent. And so you need to understand turbulence in order to understand the features that we're going to talk about today. So at some initial time t, you might see on a sphere isotropic eddies in some sense. And then at some later time, these features, because of the latitudinal gradient in the Coriolis parameter, or beta, they'll elongate in the zonal direction. And so you end up with these jet-like structures. So you can think of these as streamlines of the flow. So where in between the closed streamlines, you have very large shear, or strong relative vorticity. And so that's where we say that the entropy cascades to that small scale. So this is known as geostrophic turbulence, and these figures are from 1978. So similarly, you could actually expect zonal jets from another theory that dates to the same decade. So imagine at time t equals 0, you get this, and we're going to zoom in on that little patch. So the fluid, the basin scale flow, undergoes an instability that then results in these meridional bands. Pavel Berlov, who is one of the individuals that kind of triumphs this method, or this kind of view of thought, calls these noodles. I guess it dates back from Podolsky's work. So this is the meridionally averaged flow, and this would be the zonally averaged flow. So you can see that it gets some sort of structure to it. And then that undergoes a second instability. And so you have this theory known as secondary instability theory that predicts zonal jets as well. Maybe I should move over here. So what else can I say? So that this is like a similar structure, but it's just in terms of potential vorticity. And I show it because it kind of emphasizes that this is not what we see on the Earth, in the oceans, but maybe something more like this, where it's a weaker zonal jet flow. So this is from secondary instability theory. But a similar thing might exist with geostrophic turbulence if there's some sort of dissipation that prevents the upscale of energy. So other two mechanisms for zonal jet flow include beta plumes and radiating instabilities from the eastern boundary current. So you can imagine on the eastern side of a basin, there being specific points where the energy, there's an instability always at that location, maybe because of a point in the land that sticks out. And that then radiates energy away from it. So in Jupiter, we see patterns like this, but on the Earth, we don't see any evidence for that. Does that mean they don't exist? Our ideas of how geostrophic turbulence works and how the ocean works don't seem to agree with that. So what do we have in the way of evidence for these patterns? So recently, we've observed zonal type flows in the ocean. This is from a 1999 study using Rayfos floats, or Lagrangian drifter. So these are the tracks. And what they found was over a period of about 2 years, 1.5 years, these floats tended at depth. So this is 2,500 meters and 4,000 meters. They tended to go east or west. And so there was some sort of anisotropy to the flow. This is going to, so the red is going to be a problem. I'll just tell you that the black features in here are actually red, and that corresponds to eastward flow. So this is from a study in sea level anomaly where Nikolai Maximenko and company demonstrated the existence of jet-like structures in time average flow. So they averaged for about 4 months, and they found that out of the sea level anomaly, the geostrophic currents showed evidence of these alternating currents. So we have eastward and westward flowing currents. In a 4-month average, it's on that order.
So black is red in this picture, right?
That's correct. I'll clarify that throughout the talk. So, yeah.
Take a peek at this.
Look at my cell phone. So the same thing was done in mean dynamic topography. So understanding that sea level anomaly has the mean removed from the altimeter, Maximenko and co-authors use this mean dynamic topography, which some of the individuals in the audience are familiar with. They basically, it has drifters and other things in it to estimate, to kind of back out what the mean flow would be. Yeah, it's hard to explain. I'll just say that it has a mean flow in it. But basically, if you average for 10 years, you get something similar, where you have eastward and westward flow. And the magnitudes here are on the order of 1 centimeter per second. Okay, so similar features have been observed from Argo floats at their parking depth, so along the equator. So the dynamics here are slightly different, quite a bit different than the mid-latitudes, but nonetheless, I throw it in here because it's evidence of similar patterns. The Argo floats go up and down every 10 days. And so when they go down and they stay at parking depth, they drift for some amount of time. And from that drift, and when they come up again, when the satellite relays the latitude and longitude stuff, you can estimate drift velocities. And so that's what's been done. So this is at 1,000 meters, but they also did it for 1,500 meters. And you see similar patterns. You guys have any questions yet? Okay, so this is that same Maximenko and all study, and my advisor and myself, as well as the summer student, overlaid what we found were front detections. So we estimated the number of fronts that we detected over a very long period from microwave SST data. And when you do that and you threshold it at a certain value, you can demonstrate that these are the black dots, the thresholds. When you overlay them on the previous plot, you get patterns that are quite similar. So the implication here is that sea surface temperature as well demonstrates similar patterns. So the zonal scales, this is just kind of qualitative, but it suggests that the scale of the pattern is quite large in the zonal direction and not so large in the meridional direction. It's about 400 kilometers rather. And so this is a similar plot, but the y-axis is averaging period, and the x-axis is wave number. So this is where the peak of the energy lies as a function of averaging period. So here is about 4 years, and you still have a peak centered around 400 kilometers. So that implies a separation between alternating currents of about 200 kilometers. So several other observational studies exist, and collectively these studies suggest that there are multiple zonal jets in all ocean basins. The caveat with this, however, is that eddies can create jet-like patterns. How does that happen, you might ask? So how does an eddy create striations? Striations is the term given to jet-like patterns in sea surface height. I did not coin that. It dates back to Maximenko, but I think someone else referred to it before he did. I just can't remember who.
In fact, there was experimental study in 2002 in which they used it.
Okay, an experimental study in lab flow? Okay. So consider an anticyclonic eddy in the northern hemisphere. It has velocities on the flanks of the eddy associated with it like this. And as it moves westward under the influence of beta, you get this pattern that when you then time average, and the motivation for time averaging is to reduce the noise so that you can see the very small signal that you're looking for. When you do that, you get patterns, that's supposed to be red, that are very similar to what you might observe from the striation. So this creates a slight ambiguity in what we observe. There's a westward propagating feature, like an eddy, that's circular, does that create striations, or are the striations themselves evidence of jets? And so that's what I tried to attack in this problem. But to extend that further, Schlax and Shelton added a whole number of eddies that with random position and intensity, random amplitude and size. And when you do so, and you average for longer and longer period, so the top snapshot is an instantaneous frame, and the bottom snapshot is the time average. When you do that, you find that there in fact are jet-like patterns similar to the observed striations. So Schlax and Shelton, while they're not discounting the idea that jets exist, although if you talk to them they will, they basically created a kind of a null hypothesis. They shifted the discussion and said, well, hey, you can't say that there's jets. You need to disprove this first. You need to disprove the fact that eddies are not the ones creating it. But you know, that also says a lot of what we know from theory and from derivations doesn't really apply. It kind of ignores the physics that might underlie this kind of thing. But nonetheless, it gives us a benchmark, I guess, if you will. So this is the result of that. This is from their study, and this is a 10-year average. So they're kind of commenting on Maximenko's paper, basically. So notable consequences of the random eddy model, meaning random in position and intensity, are that eddies of large amplitude and large scale are most responsible for the striations. These eddies are few in number, and that the standard deviation of the time average field decays inversely with averaging period. That's actually a typographical error, or perhaps an error. In their paper, it actually goes as the inverse of the square root of the averaging period. So nonetheless, we can take these 3 points and try to test them in our analysis. So that becomes the center of my first study. Are jet-like features evidence of multiple zonal jets or propagating eddies? So the contribution of eddies to striations in absolute dynamic topography, you can download it if you want, but I'm basically going to give you an overview of it. So what is the altimeter? I'm not assuming that you guys are dumb or anything. I'm assuming you know a lot of things, but I'm just for clarity, I'm going to kind of go through all this stuff. So don't feel like I'm belittling you or something. So what is the altimeter? It measures sea surface elevation. Nadir looking, it looks directly downward on the Earth. From the speed of light c and an estimated round-trip travel time, you can figure out the distance between the satellite and the Earth. So imagine that an electromagnetic signal is sent toward the Earth. It propagates back up. You get a round-trip travel time, and the distance between that is given by that equation. So in reality, the Earth is not flat, and that's the signal of interest, this sea surface height elevation. So this altimeter can measure sea surface height. So the temporal resolution for US satellites, it's 10 days repeat orbit time, but for European satellites, it's 35. The spatial resolution is about 10 kilometers in the along track direction, but greater than 300 kilometers in between tracks. And there's virtually no swath width to the data. So the altimeter, basically in a short amount of time, in a few hours, it orbits the Earth like this. But over a 10-day cycle, it might make a pattern very similar to this. So why do we measure sea surface height? Well, it turns out that over the length scales and the time scales that we're interested in, these complex set of equations, the Navier-Stokes equations, can be simplified very accurately to these set of equations. So here you have a meridional current, and at V, and U is the zonal current. And P is the pressure. So we have a pressure gradient balanced by the Coriolis pressure, Coriolis force. So this is known as geostrophy. In summary, measurements of sea surface height give us estimates of, or tell us information about ocean currents. And so what I'm going to propose is that the following image, the 10-year average produced by Maximenko and co-authors, is summarized, that's funny, is summarized by a 4-year average. So we can do a similar thing by taking absolute dynamic topography, which is the sum of sea level anomaly measured by the altimeter plus a mean dynamic topography. And we can capture a similar pattern over a 4-year period. It's just that the amplitudes are a little larger. So The actual magnitudes in this area are 1.
What mean dynamic topography did you use?
Yeah, so this is Rio et al., 2011, I think it is. So I think I'll touch on that. So what I'm going to do is zoom into this area in the subtropics. In the South Pacific, it's very ambient. It's kind of nice from our point of view in that the signals, there's not too much topography that might influence things, island archipelagos. So I use the Aviso merged optimally interpolated absolute dynamic topography. It's given to us on a quarter-degree grid. It's referred to as the reference series, meaning that it's homogeneous over the entire 20-year record, or near 20-year record. And it's made up of 2 altimeters at any given time. And then this was output every 7 days. So this study was done a couple of years ago, so the data itself has been updated since then. So absolute dynamic topography is the sum of sea level anomaly, which is measured by the altimeter, plus the Rio et al. Mean dynamic topography. And then in addition, I'll use this database of tracked eddies produced by Dudley Chelton and company. It consists of eddy locations, scales, and amplitudes. So January 1993 to December 2008 will make up our data set. We apply a high-pass filter similar to Maximenko's. Actually, it's identical to Maximenko's in this study, with wavelengths less than 4 degrees. So it basically retains small scale features while eliminating the large basin scale flow. So we're trying to get at the mesoscale. And then this is just a plot of the spectral response, the filter response. So we break the record into 4-year averaging periods. We identify and remove eddies using this algorithm that I'll kind of briefly discuss. And then we compute total in eddy-only zonal geostrophic velocity that's averaged over 4 years. We'll quantify the similarity between the correlation coefficient and the fraction of variance explained by eddies. So we're basically trying to get at what is the eddy signal and what is not. And I've done this by creating an algorithm that closely follows that of Chelton and company. And so what you see here is the location in the South Pacific and the features in sea surface height from the altimeter, from the Aviso product, that have been shown to have closed contours. In addition, I restrict these features to have an eddy center in that Dudley Chelton and company did. So some things to note about this image, this result, is that not all the